Hi, good afternoon, everyone. This is Chenshu Tan. Today, my teammate Beinan Wang and I would like to discuss something about the data caching strategies for data analytics and artificial intelligence workload. And first of all, let me give you folks a very quick introduction of Beinan and I. We are currently working on both the open source Elasio and Presto DB communities, and we are actively contributing to both these two open source projects. So if you have any questions after this presentation, if you want to ping us, just feel free to ping us in the two open source communities. Maybe let's begin. So in general, we are now arrived at the big data era, which means that we are facing with a very large volume of data sets to handle. To handle this very large volume of data, there are mainly two different types of workload. One is the data analytics, which means that we want to do some data analysis on the data set to gain some insights from the data. And the other workload is the artificial intelligence. For example, we may want to train some machine learning models from the data set to learn from the data set. No matter the workload is for data analytics or the artificial intelligence, the data cache plays a very crucial role here. The cache here mainly refers to the data cache, which is used to cache files or objects. But what we have found is that, cache is really important as an accelerator for data analytics and artificial intelligence computation. But at the same time, data analytics and artificial intelligence have different traffic patterns, which means that there will be some different strategies for the cache. So that's why Beinan and I would like to give you folks some presentation about let's discuss about what kind of cache strategies that we can use to fit those two different types of workloads. And here is the agenda of our presentation today. Mainly, there are three sections. In the first section, we want to discuss about some caching strategies based on the traffic patterns, especially for AI training and data analytics with SQL statements. And then on the second section, we want to discuss a bit more advanced caching strategies. For example, we want to discuss how to plan the cache capacity if there is a limited size of cache. At the same time, we also want to share a bit about some more advanced adaptive caching strategy to fit some unknown traffic patterns. And then finally, in the last section, we would like to conclude this presentation with some takeaways. OK, so let's begin. The first one I want to introduce is the traffic pattern for AI training, what kind of data cache strategy we could use for it. And here is a very first pattern I want to share. It's about data access for the AI training. We have some key findings based on some our observations on multiple production data sets collected from some large tech companies. In general, we put them into two different scenarios regarding data access pattern. The first scenario is that the data set may be stored in some very large structured files, like an arrow file. In that case, the pattern will be the position read, or say the random reads, are more frequently than sequential reads. At the same time, the block access is almost evenly distributed. This is mainly because of, say, we may do some sampling in the training, and then we may randomly select some blocks of the data set for the training. So that's why the block access is almost evenly distributed. And then another thing is that each read from the large structured file is usually very small. Say there's a 4 kilobytes read in the arrow file. And the other type is scenario B. The data may be stored in many small semi-structured or unstructured files. This is especially common in computer vision jobs. In this type of scenario, the data file can be, the number of files may be really large. There are maybe more than 10 billion files. And the file access, for the access for each file, could be almost evenly distributed. And for each read, it may read a batch of files. So our analysis for the AI training about the cache strategy will be based on this data access pattern. And after this section, I will also share some evaluation results with you folks to discuss how the data access pattern could impact the cache strategies. So how to fit those two scenarios? In general, we have some recommendations. The first one is about performance. For data cache, definitely we want to improve the performance by using it. And one thing about performance is that we can do a hierarchical caching. Like say, like we all know in our computers, we have L1 cache, L2 cache, etc. It's the same for the data cache, which could be used for AI training. That we may do some hierarchical caching. We may have a cache on the local like training node, and we may also have a cache, remote cache, to serve some more large volume of data remotely. And another thing, as what we have mentioned, is about like positioned or say random arrays. We can also do some optimization from it. Usually, what we can do is that we can do to read the cache by chunks in a fixed size instead of by a random size given by the client. And here is a diagram, a small figure that I show in this slide. Let's say, suppose that the client would like to fetch a data starting from the offsite 1 megabytes. And the size that the client would like to fetch is like, say, 100 kilobytes. But what we may return is a chunk by 1 megabytes. Let's say, in that case, we'll directly return the block starts from the offsite 1 megabytes and ends at offsite 2 megabytes. So 1 megabytes, that's the chunk size returned to the client. That will help us to reduce the request number in a position rate when position rate or say random rates are more frequent. But at the same time, it will also bring us with a problem that is called rate amplification here. Still take the example that we have discussed. The client may just want 100 kilobytes, but we return the client with 1 megabyte. So that's a 10 times rate amplification here. So that will be some trade-offs here. Like say, we may want to reduce the request number, but at the same time, we may increase the rate amplification here. So that's a trade-off that we really need to care about in the practice. Another key point is about scalability and elasticity, because we want to let the cache to fit these two different scenarios, scenario A and B. In that case, we need to give the cache the ability to grow or shrink capacities. And at the same time, there are different like design principles for that, like different architectural design for that. One is masterless, and the other is the master worker like kind of pattern for that. And those are two different patterns, and we may use either of them in the cache way to serve the different things. Yeah. Okay, so that's the first pattern about the data access. And another pattern we want to show about AI training is that we also noticed that in recent decade, or say especially in recent, like say 5 years, we have witnessed a growing demand for the cloud. In that case, there is a moving like a strategy that to move the machine learning infrastructure from on-premises environment into a cloud environment. So that will be a hybrid or multi-cloud environment to serve the machine learning infrastructure. And here is a very general idea of the hybrid or say multi-cloud infrastructure for machine learning infrastructure. Say on the left, there is a training platform. It could be an offline training platform. And then on the right, there is online, like could be an online machine learning serving platform. Say in the middle, there is a storage. The storage could be used to store the data sets or the models. And then for the first step for the training, the training cluster will need to read the training data from the remote storage. And the cache, a unified cache layer could play a very crucial role here, that the cache will be responsible to load the data set first from the remote storage into the cache, and then feed the data set into the training clusters. On the other side, when the training jobs are completed and the models are written back to the remote storage, there could be a unified cache layer on the serving platform that this cache layer will be responsible to load the models first from the remote storage and then feed the models to the serving clusters for other like serving purposes. So that's kind of a general pattern of that. So what kind of suggestion that we may want to give you folks for that scenario? There are mainly two things that we want to mention here. One is that because this is now a hybrid or say multi-cloud environment, we may want to make the cache be cloud-friendly. So it may need to provide some flexibility for hybrid or multi-cloud environments. And at the same time, we may want to provide some configurable cache admission and eviction policies. Another thing is availability. Like say what I mentioned, the cache may be used to load the models, to load data sets. We need to avoid single point of failure here. And also let the cache to support fallbacks to end the storage in case there is some cache miss or the cache is offline. So here we want to give you folks a very general idea of like how we could integrate the cache with the AI training platform. Like say we have a training node which is running some training jobs. And then we have a cache client which is deployed in this training node. And then in the middle, we have a remote cache cluster. And there could be some multiple cache workers there to serve the cache. Then the training node may want to like read a specific data set, and it will talk to the local cache, the cache client here. If it has a cache, it will just return it. If it doesn't have this subset of data set, it will talk to the remote worker node to get the data. If the worker node has the data, it will return it. If it doesn't have it, it will talk to the end storage to load the data into the cache and return it to the training node. So that's a basic idea, like how we could integrate a cache with AI training to speed up the AI training jobs. And then here, we want to give you folks some evaluation results based on the patterns that we have discussed. Remember that we have scenario A and scenario B. So let's discuss them one by one. The first scenario is that the data is stored in some large structured files. And then what we have done is that we evaluated on a production machine learning data set, and we reapply real practical traffic pattern onto it. And on the right side, we drew a diagram about the results. And we differentiated position rates and streaming rates. The blue bars are from the position rates, and the red bars are from the streaming rates. And what we could observe from the results is that you see the blue bars are generally lower than the red bars, which are the streaming rate. So for the scenario A, when the data set is pretty large, they are large structure files. And then the data access pattern is that position rates could be more common than like sequential rate. In that case, what we could observe is that position rate outperforms streaming rate when reading such type of large machine learning data sets. And what about the scenario B? What about, say, I have a computer vision jobs that I want to train on a large number of images. Like those are small and structured files, right? We also evaluated on that. We have a production data set collected from a tech company. The original data set is very large. It has more than 10 billion files in it. And we choose a subset of it. So the subset has a bit more than 10,000 files in it, and each file size is around 100 kilobytes. And then we also ran the position rate and streaming rate against this data set. And here is the result on the right diagram here. So still, the blue bars are from the position rate, and red bars are from the streaming rate. And what could we observe from this part is that the streaming rate looks to be a bit outperforming than the position rate when reading such small number of position rates, a small number of machine learning data sets, which means that the position rate may be helpful on the scenario A, but for the scenario B, when there are a large number of small unstructured files, we may still use the traditional streaming rate to help us to load the data set. So here is a very general idea of a future direction. Because today, for our presentation, not only we want to share some experience with you folks, but we also want to discuss some future direction with you folks. Like say how a data cache could play into a machine learning life cycle. We have discussed some like data access patterns, some traffic pattern, so how to integrate cache with AI training. But maybe we can go even a bit further, that we can integrate a unified data cache layer with different components in a machine learning life cycle. Like the components could be data preprocessing, feature engineering, model training, or model inference, or say model serving. Like say, for example, after the data preprocessing, the processed data could be written back to the cache and then be synchronized with the remote storage. For the feature engineering, they could get the processed data from the cache and read back the features into the cache. And for the model training, the training clusters could read the data set and the features from the cache and read models back to the cache. And for the model serving, it could be the same. Like they could load the models from the cache and also store some query results into the cache as a query cache for the cache. So that's a possible future direction, and we have also witnessed some like research papers published in this domain. And then I want to introduce my teammate Beinan to talk a bit more about the traffic pattern for SQL statements.
Hello, everyone. I'm Beinan from Luxio and the PrestoDB community. So firstly, I will share the traffic pattern for the analytics workload, and then I will share something about the cache planning and how to use the cache filter to improve the cache hit rate further. Let's start with the traffic pattern of the analytics workload. So based on the early research we observed in Twitter, we are seeing the majority of our query, actually, they just read only. They just read the data from the remote, but they won't write any data. And also, the amount of data they read actually is unbounded. It can easily to go to maybe 20 petabytes or maybe 200 petabytes. It might cost a lot. And the third thing we observed is, as I mentioned, because we separate the computer engine and the storage, a lot of data reading actually is from remote, from another data center, maybe from another cloud storage. And also, we observed, no matter it's a Presto or Spark, they may have a lot of temporary file written to the storage, but some of them maybe just got renamed or got deleted after your job or query finished. And so based on this kind of traffic, let's go into the details of each request, maybe each query. So we found for many queries, just for the first table on the top, we are seeing for the data read, it just read a very small piece of data from the data source. That's because the majority of data source is a Parquet file, awk file, or error file. If your query is highly selective, they won't read the entire file. So it just skip the read. So you can see for each read, probably they just read 1K, maybe 1 terabytes plus 600 bytes, something like that. And also the read latency, we can see a long tail of the read latency. And also, as I mentioned, because we are using a structured data, we are using columnar data, so the read for each read will be very small. The lower table actually we collected from some internet company. The majority, around 95% of read, is less than 1 megabyte. And also you can see the majority of the data read actually is less than 64 terabytes. So based on the traffic pattern we observed, when you want to apply or deploy a cache, we highly recommend to select a cache, or maybe design a cache with a multiple cache layer. You can have a in-memory file buffer per thread per file, and also you can, under the file buffer, you can have a page cache, maybe 1 megabyte page for each cache unit, stored in your local NVMe. For this tool, you can get a better performance, but the cache capacity may be limited. So in this case, you can deploy a remote cache, a separate cluster just for better cache capacity. And also, because we're talking about the majority is the structured data, so there's a lot of skips. So we need to optimize for the sequables input stream. So probably you may need to preload the data, but on the other side, we also have to reduce the read amplification. Okay, so the Python 2, also, as I mentioned, no matter the Presto, Spark, Trino, they are trying to read the data from remote. They separate, the idea is they separate the compute and the storage. So they're always reading the data from another storage. So here's the thing. If you want to read the data from something remote, the I/O bandwidth, the network latency may cause the issue. So in this case, we have some other ideas about the cache optimization. For the first two, I think already got well discussed by Chunxu. We need cloud friendliness, we need availability, there should be no single point failure at all. But I would like to mention about the cost-effective things, just because, as I mentioned, the the data load from the remote storage could be unbounded. They might have some super big query, just one SQL can scan maybe millions of files, and it's a lot of API call. But you all know, right? The remote storage, the S3 or something else, the cost is based on the number of API calls, right? So you can use that cache. But here I would like to mention here is just, we all know the cache can reduce the number of API calls, but it's not always true. For some case, if the cache hit rate is low, maybe you can see some read amplification because the cache is based on some unit, right? Maybe 1 megabytes, maybe 64 megabytes. If you touch 1 byte, most cache will fetch 1 megabyte or 64 megabytes for you. So in some case, if your query is highly selective, you might see 100 times of the read amplification. That will give you some trouble for the cost. And also the temporary files may be another trouble. Some query or some computer engine may write a lot of temporary files, intermediate results, to your storage. But if you're using some storage on remote, it will cost a lot. But I believe most of the temporary files got deleted before your query finish. So probably you can just use a cache to store your temporary file. Here is how we integrate Elastic cache with something like Presto or something like Spark. So we just build in a client-side cache, just running in the same process or the same thread of your computer engine. We put a file buffer, and also we put a local page store. We call it page cache. That's on the client side. It will use the memory and the local disk of your compute node. Because most of the computer engine, their worker node, maybe for the modern ones, they don't really need the local disk. So you can just take advantage of their local disk as a local cache. But if you want a better cache hit rate, you need a separate cache cluster just for a large cache space. So I think that the first two, the file buffer and the page cache, can give you the best performance, and the separate cache cluster can give you a much better cache hit rate. Okay, here's some evaluation. I think that the evaluation had been made earlier this year. So at that time, firstly, we tried, the top chart is something about the query on the text file. Because the text file in Presto is more like unstructured data. It will load the entire data because there's no index. It just reads the entire data sequentially. We found by enable the prefetch, it's a default feature in Alexio, so we can get a huge performance gain. Because some queries improve the performance latency maybe by 100%. And almost every query got some performance gain. But the Presto actually is a CPU bound, so this kind of improvement is really huge things. But on the bottom, the other side, actually that's the majority of the use case, is the Parquet. We didn't see much performance improvement. Why? Just because they have a lot of precision read. So in this case, because there's some read amplification, so even you touch 1 byte, the cache will trying to load maybe 1 megabyte or 64 megabytes from the remote. That's caused some degradation of the performance. So at that time, we didn't optimize the precision rate, but now I think we already have it, but maybe you can just, we are open source, you can just download the newest code to give it a shot to see if it's any better than this one. Okay, so the previous section, we are talking about the cache hit, how to design a cache. But the evaluation and also the assumption is made by the cache space, the capacity is sufficient. You always have enough cache space, but actually it's not true because your memory or your local disk, especially for NVMe, is super expensive. So mostly, I think we need to do a cache planning. You need to make a decision. How large cache we really need for your workload. You cannot put everything into your cache, because your cache is more expensive. So here we will push the problem further. Sometimes because you have a shared cluster of Presto or something, multiple data owners, users, or maybe you want to push different cache policy for different tables or something. You need to know which kind of data or which kind of table, which file is more valuable for the cache. But it's really difficult to know, right? So we designed a tool version of shadow cache. The first version of shadow cache we made is made by a chain of Bloom filter. I think most of you is in the data area, so I assume you know the Bloom filter. But anyway, they just use a very small amount of memory to tracing a large number of working sites. So here we use Bloom filter to store the cache ID, which means we can counting the unique data access, because maybe your query to touch the same file again and again, but the file ID, I mean the path should be the same. So using Bloom filter, we know, okay, in a short time period, we touch 100 files, and on the other 6 hours, we touch another 500 files, whatever. And also, we can counting the bytes we cached. I mean, not cached, the bytes we accessed. So by our observation, we use a very small amount of memory, 65 megabytes, to tracking the 6 terabytes working site. So here we know the working site, then we can do the cache capacity. We will have a decision tree later. So it's the second version of the shadow cache. We are using we call the Cuckoo filter. And the memory usage is a little bit larger, but the result is more smooth because we're using a single Cuckoo filter with a counter to track your working site. So the chart on the left shows the working site estimation. And maybe in 24 hours or in each 6 hours, I mean, how much data you touched, unique data blocks you touched by Presto or Spark. And on the right side is the cache hit rate. I think it's too small to watch a little bit. Okay, the right one is the hit rate for the shadow cache, which means if you have a limited cache space, but actually it's not true, what the cache hit rate is. And the blue one is the real cache hit rate. You can see when your cache is healthy, these two cache hit rate is always very close. With some exception, maybe you have a large query to fetch the cache or something. So this one shows the healthy part. And okay, here's the decision tree, as I mentioned. Now we have some stats about your shadow cache. We also have some stats about your real cache, the working cache. So based on the stats, we can compare these two. Firstly, we can check the cache hit rate of your shadow cache. If the hit rate of your shadow cache is already low, it's very low, which means the cache won't help. Your query, your traffic pattern is not very cache friendly, which means if you're adding more cache, it won't help. It won't help at all. So on the other side, if the shadow cache hit rate is high and the cache hit rate, the real cache hit is low, which means you can do something, right? You can do something. Then we check the cache usage. The cache usage is true. If the real cache usage is larger than the shadow cache or something, or equal, which means your current cache is overloaded. So you can just add more cache space. So on the other side, if the both cache hit is high, and also we can take a look at the usage of the shadow cache and the real cache, sometimes we may find your cache is underused. So which means you can shrink your cache cluster. You can save your money. You can reduce the cache space maybe from 1 terabytes to 500 megabytes, but with the similar cache hit rate. Okay, so based on the Cuckoo filter and the Bloom filter we just talked about, we also invite some cache strategies. We call the adaptive cache strategy. So it's quite simple. We just put a cache filter before the cache manager. So which means when you got some data, when you got some real data, you have no idea if we should put it in the cache or not. So in this case, we check the counter in the Cuckoo filter or Bloom filter to see, okay, this one already had been there for a couple of times, maybe a greater than a threshold. We can just put it into the cache. Otherwise, we reject it. Because it's running online, so we can always take the new data and do the judgment to see which kind of data should cache or not. On the other side, if you really don't want to maintain something in the memory, you can use something like offline training work. You can collect the trace of your cache and train a model to decide which file should be cached, which file should be not cached. But here, we won't track for each single file. Mostly, we just track some prefix. If you're using Presto or Hive table, we based on the partition, the key of the partition, to decide which partition is more valuable to cache or not. Okay, the last section is the takeaways of this presentation. So the first takeaway we believe is the position read, because the majority of the read or the data source it's a structured data, and particularly it's more like a columnar data, like a packet, like ORC. The data read on this kind of files is highly selective. You need always skip the things. So in this way, the cache, if you design a cache or you apply a cache, this one should be fully optimized by this kind of position read. We should eliminate the read amplification in this case. The second one is the cache in the worker node, which means if you can develop some local cache, just running in your Presto worker or the PyTorch node, whatever, it can highly improve the performance, because the data will just load the data from the local disk. But in this way, you need to hack or improve a little bit about the scheduling of your Presto or maybe something else to make sure the same file will always assign to the same worker. But again, the local disk may be, the space for your local disk may be very limited. So if you really want a higher cache hit rate, you still need a separate cache cluster. But anyway, because modern computer engine, the local disk is just free. They're not really using it, so just take it as a local cache. I think it's helpful. And the third one is our team, Alexio, we are trying to use some Bloom filter, to use the Cuckoo filter, to tracking the working side. We provide statistics of your traffics, and you can get some rough idea about how big of your working side, and also we can provide table-level working side estimation. So I think this kind of information will be valuable for your cache planning, save your cost, and improve the cache hit rate. The last one I would like to mention is the adaptive cache strategy. It's our potential research direction. Actually, it already has been there for years, but we are still working on it. We will develop more online and offline caching strategy, but just based on the data structure and the trace we have now to improve the cache filter and the cache hit rate further. I think that's here's the last page is the reference. Some of the data we collected based on the paper we posted earlier, and some from other research. Yes, so I think that's all.
Great session, everyone.
Thank you.